I'd also like to thank the organizers for inviting me. I'm going to give an update on the efforts mostly being undertaken by the science working team or group on studying massive black hole binaries and parameter estimation, in particular what impact the change of the design from classic LISA to E-LISA, LISA-like is going to be. So just a summary of the topics I'm going to touch on. So rather than just leaping right in and throwing lots of numbers at everybody, I know not everyone in the audience is intimately familiar with all the details of how we calculate these things, so and what matters as far as improving parameter estimation. So I'll highlight some of the features of the whole process, waveform to detector, etc., that really matter the most as far as what parameter estimates we get. I'll talk about how those features, those specific elements that matter the most are changed in the redesign, and what impact quantitatively that has. So I know as Antoine said, it's sort of morbid and not super useful to compare to old LISA, since we don't have old LISA, we never had it, but it's a baseline that people are familiar with and something to touch base with. So I'll do a little bit of that. What can we do with a LISA redesign? Or more accurately, I'm going to highlight what things perhaps we can't do and what is needed to get back those science goals from original LISA. So first, a very brief primer on what goes into these calculations, and all of them are fairly similar. You're seeing different plots by a fairly sizable community of people using different codes, etc. So I'll try and highlight some of the universal aspects before I go on to the differences. So everybody needs a waveform model. Here's a bunch of waveforms. So it needs to be parameterized, so you need to have a clear functional dependence in terms of physical parameters, because you want to make a Fisher matrix in terms of physical parameters that agrees with the parameters everyone else is choosing. So convenient way to divvy these up. This is not standard nomenclature, I don't think. This is just what I think of. In numerical relativity, these are the guys that we need to run a new simulation for, and these are the ones we don't. So extrinsic, I'm calling anything that we can just rescale the waveform. Take a single waveform in geometrized units and apply some scaling and have a new waveform. These ones, this is where the parameterized model comes in. You need to encode the functional dependence of the strain, the geometrized strain, in terms of these. And there are various ways to do that. You need to model LISA, so you need to know how LISA, or now E-LISA, which is going to be slightly different, how the interferometer is going to respond to a gravitational wave, how it's going to respond to noise, what the noise levels are, etc. So that's where these configurations come in, setting the noise levels and such. We apply a response. So the response function in particular, I'm going to highlight later, as something that could be important for parameter estimation. And then finally, calculate uncertainties. It's been mentioned that almost all the numbers that are being thrown at you are calculated with the Fisher matrix. Now, it's as large as 17-dimensional now that we're including eccentricity. And we know the SNR has gone down some, and the errors are getting larger, etc. So the validity of this approach is we're pushing the limits. So it's important to validate these things, and this is a nebulous statement because basically quoting Antoine here, so you can tell when I put this talk. So MC validation is ongoing, so that's a critical thing, and you know, it's being undertaken to make sure that the estimates we're getting out of this procedure are accurate. And as John said, this is just Fisher matrix is just matrix of the derivatives of the waveform with respect to the parameters. You know, all the inner product combinations of them, and then we invert it to first order in deleting order and inverse SNR to get the errors that I'm going to quote you. Okay, so that's fine. That's how we calculate it. But as far as that Fisher matrix is a derivative of the waveform with respect to parameters. Well, what are the things that influence that physically? How does this structure of the waveform arise? What are the important things to consider? So first, you have intrinsic parameter dependence. So that's what I was mentioning before. Q, S1, S2, and E. These are vectors. So this is, in your model, you have to have these parameters parameterized and know how the waveform in non-astrophysics units, in general relativist units, depends on these parameters. And here's the waveform going in and interacting with Lisa. That's a puncture track. So, this slide took the most time to draw this thing. So then we have independent waveform channels. So this is, we all know, initially Lisa was 3 spacecraft, 3 optical benches, 6 links. So the issue, one of the main concerns with the redesign, as most or all of you have heard, is this going from 6 links to 4 links, turning 2 of the spacecraft into just transponders, making the setup more like LIGO in space type, a single LIGO in space type thing. So we'll only get 1 channel of information in that case. So naturally you could imagine we get more information in 3 channels than in 1. Doppler modulation. So the Lisa constellation is orbiting. At least with Lisa, the signals are on for potentially as long as you're observing. So you get that modulation on the signal as you're moving toward the source and away from the source, and you can use that to separate out the dependence on some parameters from the dependence on others and break degeneracies. And then finally, frequency dependence of the response function. So it's interesting with Lisa that, so as the wavelength of the signal is becoming the same scale as the interferometer, you no longer have a fairly trivial response. You start having more complicated structure. And this is true for any interferometer. It would be true for LIGO. The point is this happens at a point where the interferometer is fairly insensitive. In the case of Lisa, this is happening where you still have, within a factor of 2 or a few of the best sensitivity we would have in the bucket. So this can potentially be important. So how does the redesign affect those 4 items that I highlighted? And you could come up with more subtleties that affect things. But so the intrinsic parameter dependence, obviously, that's not affected. When I say intrinsic, I mean literally on the source end, what's getting shot out into the sky for Lisa to see. So that doesn't care what Lisa's doing. Independent waveform channels, well, that's a big one. So we're going from 6 links to 4, only 1 data channel instead of 3. One of the big questions is, okay, do we lose science with that? Obviously, most of these choices are made out of necessity. So, no one argues that 4 links is better than 6 for science, which is, sort of something that we have to do, or may have to do. The Doppler modulation, that's also potentially a problem for some sources. So we've shortened the arm lengths. That moves the sensitivity curve over to higher frequencies and lower masses. So lower mass sources chirp faster. So whereas before you had sources in band potentially for the lifetime of the mission, or at least order a year, you can have some of these sources in band for much less time, so they're not benefiting from that oscillation, or they're not benefiting here as much. Frequency dependence. So again, we have shorter arms, so that moves the response to higher frequency, the deviation from low frequency approximation to higher frequencies. But sensitivity moves over also, so it's sort of a wash in the sense that a different mass range is going to be affected most by this now than it was with classic Lisa, but it's still going to be important. Okay, so before I get into the parameter estimation, you've already seen plots that look like this. So Emanuele-Berti and other worked on this, and this is one from the Goddard group. So the main point I wanted to make here is for the theoretically expected distribution, so that these SNR values pay no attention to astrophysics. So they're totally model agnostic. It's just if there's a source in nature and it's there, that's the SNR. But first of all, these are at redshift 1. If you, well, I'll wait. In the next slide, we'll say this. But rather, if you look at the mass and mass ratio range that one might expect based on theoretical grounds from simulating these populations like Alberto and Marta do, you see that it's really only a factor of 2 or so difference in SNR. Comparing apples to apples, you can get another square root of 2 if you allow Lisa to be 6 links and say, okay, the redesign is 4. The point has been made that Lisa was never necessarily going to be 6 links. It was just a possibility, and nominally it was 4. So to be fair, compare apples to apples, and it's really just a factor of 2. And the reason I make this point is parameter estimation is more than just SNR. Sometimes the scaling works. A lot of the time the scaling works, and it's very useful and handy. Unless you add new physics, then the scaling probably doesn't work at all. Okay, so distribution of sources. So obviously an important question is, in these theoretical studies that Alberto and others do, where are most of the sources thought to live? Because that'll deter, if we measure sky location and luminosity distance phenomenally well at Z of 1, and there's no sources at Z of 1, then that's not very helpful. So the main point to make here is number of events in some redshift bin peaks around redshift of 5, whereas the fiducial choice for calculating these things is often redshift of 1. So we need to bear that in mind when we're calculating these things. So this is classic Lisa. And the Y scales are going to be the same. I'll flip, stare at this plot for a second. This is classic Lisa, and I'll flip to configuration 2. So the most dramatic change is sort of in the redshift 1 to redshift 4 regime. The number of, the fraction of events detected drops. But the peak is still around redshift 5. Qualitatively, this is similar. Which is not altogether surprising. Okay, so that's what we expect as far as what nature will provide, and sort of highlights how we calculate these things. So I mentioned in the previous slide that one of the things that goes into the calculation is obviously the model of the waveform. So we have a variety being applied to this problem. The science working team has something like 5 groups working on complementary waveform models and approaches to the whole process. So we have several groups. highlight them. I apologize. I know I'm going to miss some people or not appreciate that. That would help. Okay. Not appreciate that some people are doing multiple efforts and I missed them, so I apologize in advance. Two groups at least have done calculations looking at in-spiral waveforms, so not including merger and ring down, but including spin precession. So I'm not sure if they're to the same order. They may be, but I imagine they're spin precession, spin order. I'm not sure actually what order these two efforts are respectively. By order, I mean post-Newtonian order, how many terms they're including and such. But some amount of spin precession, as well as higher harmonic content. So waveforms, are dominated by the quadrupole mode, oscillating at twice the orbital frequency, but there are other components. And the less symmetry of the system, the more of those components get excited. So if you have unequal masses, if you have spin included at all, if you have eccentricity, then
Did Antoine do this? I thought it was jets from flying with the other group. I didn't think Antoine had done spin precession for Antoine's.
You definitely could be right. I thought on the wiki the list was Antoine.
We did spinal precision.
Yeah, I think did you do that? I don't think so.
Okay. Yeah, please correct me if I'm misattributing things or what have you. So that's as far as a set of physics being applied. That's being applied by two groups, one of which may be misattributed right there. So another group is looking at in-spiral merger ring down. So the difference being they have mergers and ring down with line spins. But whereas this effort has higher harmonic content, this one doesn't. And whereas this one has precessing spins and precessing orbital angular momentum vector, this one doesn't. But it has mergers and ring downs. So again, complementary efforts. So the group I'm part of is looking at in-spiral merger ring down with line spins, but now including the higher harmonics. But again, aligned spins, so we don't have the spin precession. Then another effort by Neil and Ryan Lang, in particular. I'm not sure if there are other people involved, but I know at least Neil and Ryan, looking at spin precession and higher harmonics in the in-spiral, along with a merger that I believe is it's a line spin and it doesn't have higher harmonics. That's my understanding. Again, it's sort of nice that all these are complementary. It would be even nicer if all of them got put together. So that's, I think, the goal is in-spiral merger ring down with spin precession and higher harmonics in the in-spiral, and align spins with higher harmonics in the merger. The reason I say align spins is at some points there is no spin precession as you're transitioning from a space-time of two black holes to a space-time of one black hole. There's no second spin to have precession with. So the dynamics almost certainly becomes dominated by some single spin quantity, most likely the projection of the individual spins on the orbital angular momentum vector. That seems to be fairly promising as far as assuming that caveat and then comparing to actual numerical relativity waveforms. But all this stuff is very preliminary. So whereas this stuff has been, all these other efforts are very old and vetted in that we've been working furiously on them for weeks and weeks. So the point being, none of these are necessarily have been around for years. Some of them have. But this effort, I think, is fairly even more recent. Okay, so also variation in noise and response. By variations, I don't mean variations of the noise and of the response. I mean among the different groups, different ways of handling these things. So each group has to model or simulate the noise. I would guess that everyone models it. In principle, one could either just calculate a single instantiation of the noise and use that. The problem potentially with that is there's lots of fluctuation in the noise, so there's structure in the noise. So you can potentially think you have parameter information from the noise. And you would if you knew that the noise was going to take that shape all the time. But the point is you don't, it's just a single instantiation. So this is a comparison for our approach in particular. So we're using synthetic Lisa by code written by McWilliams to apply the response. And so this is just a comparison of, we use an analytic model, but just as a sanity check, I ran a bunch of actual noise realizations and averaged them down to make sure things agreed. And all the groups are doing that for their various approaches, sanity checks to make sure everything is sensible. So each group uses essentially the same observables. So we have, a one-link Michelson interferometer, so an X observable, or a six-link AET kind of set of observables. The response is handled slightly differently among different groups. You can treat it in the frequency domain, which has the advantage of, I suspect it's more stable. There's some issues with stability that get aggravated when you do things in the time domain. By stability, I mean taking numerical derivatives in particular. But the frequency domain approach has to be approximate, so that's a downside. There are also ways of treating the response exactly or approximately in the time domain, both of which are being done by different groups. The hope, obviously, is everything I just said is irrelevant, and none of it has any impact on parameter estimation, but I don't think that's been demonstrated, so it would be nice to do that. Okay, so now on to the errors. So that's a primer of everything one would need to know to interpret these results. Now you know everything that goes into them. So I'm going to show you some results from the different groups, and I'll try to walk through because I know just throwing some data up is fairly confusing. So first of all, ignore the blue curve. I mean, it's one of the redesign configurations, but the one I want to emphasize here is the green curve. So the green curves are configuration 2 of the Lisa redesign, so it's one of the more likely redesigns to be moved forward with. And then the red curves are Lisa. So you probably can't read this or see this at all. So you can see these are all functions of redshift. So uncertainties are increasing with increasing redshift, as one would expect. The luminosity distance is one that's of particular interest, and I'll focus on later. But you can see, whereas classic Lisa was starting with a fractional luminosity distance error of order 10%, and climbing up to 50% around Z of 5, Z of 6, and then beyond that, it would be lovely to put that data at even higher redshift to good use, but I'll talk a little bit about that later. It's not absolutely clear that we could, but certainly up to redshift of 10, and then maybe beyond that, we don't expect anything to be there. But it's still nice to know that if anything's there, we can measure at that level. So the redesign, on the other hand, starts at a redshift of 1, already above 100% error, and then rises. This is a specific model. Everything that I show, bear that in mind. So this is Stas and his collaborators using the inspire merger ring down with the line spins, but without higher harmonics. So, bear that in mind. Here's a plot that Alberto sent around. I'm not sure who was involved with making it, but Alberto's been collaborating with several. And again, this is a very communal effort, so different people are contributing to different things in different ways. So I'm not sure that the attribution is super critical. Just to know that everyone is working hard. So this looks at the fractional error in redshift. And what we're comparing here is a 6-link LISA, 4-link LISA, and that same configuration I just showed, configuration 2. So this is a similar quantity to fractional error in redshift, like I showed you previously, particularly at low redshift. So you can see for original LISA, we've got a peak at point a few, so 10, 20, 30%, something like this. Whereas configuration 2, that moves over and is safely on the wrong side of 1. So that can pose a couple of problems for the science goals. And again, I'll tell you why I'm beating this parameter over the head. But this is another result with another code that may again be misattributed. So this is looking at a 6-link LISA with the green curve. 4-link LISA, I haven't mentioned configuration 5 yet, but that's, we were directed that configurations 2 and 5 were the most important to run. So basically everyone ran on at least those 2, and some were ambitious enough to run on everything. So this dark blue curve is configuration 5, light blue cyan is configuration 2 with 6 links. So that's an apples to apples comparison with the LISA 6-link value. And then this red curve is the interferometer we have, or we're planning to have. And again, we got fractional error in luminosity distance, up around 1 for the redesign, whereas an order of magnitude lower for original LISA. So, I'm sorry, this is kind of overwhelming. I'll try to explain it. So the next 2 slides are results by Neil and Ryan using their processing inspire with higher harmonics, and tied on to results for an aligned spin merger without higher harmonics.
It's also with Amaro-Seoane.
I'm sorry?
It's also with Amaro-Seoane.
Emmanuel, okay.
Yeah.
So looking at that, I think the confusion why someone else did that too is the PDF had your guys' names on it or something like that. So that's what's that? So yeah, Emanuele has worked on. If I didn't mention, he also did the SNR plots. He's been integral in all of these efforts. So definitely keep him in mind. So this is looking at probably the most critical parameters, or the most interesting astrophysically. So individual masses, luminosity distance, and these are, I'm sure, fractional errors, and spin parameters 1 and 2, and sky ellipse area, the error ellipse in square degrees. So this top plot is the large C deficient accretion, and I know one of these is configuration 2, and the other one is LISA.
No, they're both configuration 2. The blue is without merger ring down.
Oh, right, that's right.
And the red is with merger ring down.
Right. So the thing to compare here is this is trying to basically isolate the impact of the adding on the merger ring down. So you can see masses, and we're going to have a discussion session where one of the questions that's going to be covered is how accurately do we really need things like mass and spin magnitude and things like this. So you can see with merger ring down, it's a fairly broad distribution, but as high as a 10% fractional error, as low as 1,000th. Whereas without merger ring down, I imagine astronomers could do better if given an error smaller than 20 or 30%. But that's something I would like to hear about when we have the discussion session. Again, luminosity distance without the merger ring down, we're again seeing this fractional error of 100%. With merger ring down, we're starting to creep back below that to many tens of percent, which this is encouraging because we see with our code similar results when we do the same type of comparison as far as relative differences. So as far as sky angle, we're going from thousands of degrees, so very roughly take the square root of the number if you want to know actual errors of each dimension. So basically the punchline with all of these is the merger is contributing significantly at the, say, order of magnitude level. And again, with the small efficient accretion, basically the same conclusion. So I don't want to linger too long. This is with the chaotic accretion. So the difference between the two, which is explained, but I'll just reiterate. So the efficient accretion imagines that the gas is coherently flowing in the same direction as the spin, I imagine, and just ramping up the spin of the black holes. The chaotic accretion is incoherent addition of angular momentum, and so the spins will tend to be lower, not necessarily aligned with anything, whereas the efficient accretion will tend to be aligned with the orbital. So, yes. 10. Great. So, what might be a little bit surprising so the luminosity distance, again, the same picture without mergers. The errors are slightly better than the efficient accretion case without mergers, but here's this blue curve, and it's again roughly peaked at 1. When you include the merger, it pushes down some, but it's a very similar picture, which might, at least to me, is a little bit surprising, given the differences in the populations. But I would say this kind of says that the spin is not critical to this, but maybe that's not a fair conclusion. Again, very similar picture to the efficient accretion of the sky angle. And I didn't touch on the last one, but here's spin magnitudes. So for the smaller spin, these aren't equal mass black holes. I'm not sure where the distribution is peaked, but a few to 1 or 10 to 1, something like this. So the larger the mass ratio, the less influence this other spin has on the waveform. So it's not surprising that it is really poorly determined, at a factor of 10 level. When you add the merger, it's nice to see that you get down to 100% error. So you're somewhere in the ballpark of knowing what the spin is. And with the larger spin, things are a bit better because that one is the one that's having more of an influence on the waveform. And it's a very similar picture for small seeds. So let's go ahead. So this is the Goddard and UMD and me at Princeton efforts. Just looking at the large efficient accretion catalogs here. You can see the SNR, so you have a square root of 2 factor going from 4 to 6 lengths. The higher harmonics are essentially irrelevant for SNR, which again emphasizes this point of the SNR scaling doesn't. So naively, you could look at some results for a given waveform and say, oh, the uncertainty is such and such. Well, if the SNR is some value, the error scale is 1 over the SNR, so I just throw that in. But that's only valid if you're not adding new physics. But that difference in SNR has to just come from changing the luminosity distance or something. luminosity distance, because that's particularly interesting. So without the higher harmonics, so these all, unlike the plots from Neil, all of these have merger. The distinction here is the number of links and the presence or absence of higher harmonics through the whole waveform, so in the inspiral and in the merger. So the blue curves are 4 links, no higher harmonics. The green are, again, 4 links, but now we've included higher harmonics. And then the red curve is the wished for 6 links with the higher harmonics. So the comparison here is really green and blue. So you can see, a factor of 3 improvement or so in fractional luminosity distance error just from doing that. There's some influence, but not a ton. This is ecliptic latitude. You see a gigantic jump, as well as a striking change in the shape of the distribution, but the width of the distribution. But going to 6 links, which makes sense, right? I mean, so if LIGO only had the Hanford Observatory, we'd have no idea where anything was coming from. So, but it's encouraging that there is some level of improvement just adding the higher harmonics. So these are some more parameters. So this is the ecliptic longitude, very similar picture to the latitude. These are some angles. One thing I will note, this is the error in inclination angle, and it's noteworthy that, so this is, again, the curve for no higher harmonics and 4 links, and the green is the curve for adding higher harmonics, but still having 4 links. So you can see the improvement from just doing that brings you almost all the way to the 6-link part, which is suggestive because one of the limiting issues for the luminosity distance is that it's very covariant with the inclination angle. So that might go a long way to explaining why the higher harmonics improve the luminosity distance. And this is time, which is not super interesting. Mass ratio. So there is some improvement adding higher harmonics and then going to 6 links. Very little improvement in the spin magnitude doing any of those things. So why did I focus on DL so much? I tried to give you some numbers for other things, and I'll say them again at the end. But why focus on luminosity distance? Well, one thing that has or had been a hot topic is cosmology, constraining the Hubble constant, constraining the equation of state parameter, things like this. In order to do that, at least in order to do that with LISA, one needs to combine an electromagnetic measurement with the gravitational wave. So the gravitational wave is going to give you the measurement of luminosity distance. You assume the electromagnetic counterpart is going to give you a fairly precise measurement of redshift. So whatever the counterpart is, it's something that you can go look over there and identify the host galaxy. So once you do that, you know the redshift. So it really comes down to how much error is in this luminosity distance, and we already discussed that the redesign hurts that. I made this number up. People can argue and they'll be right. There are others who know more about this, but you need to have 100% error in the luminosity distance is not useful for a couple of reasons. So if you want to look at structure formation, you want to know what mergers are happening in a certain redshift epoch and a certain luminosity distance epoch. Say Z of 7 to 10, and Z of 4 to 7, and Z of 1 to 3, some sort of intervals. And to do that, if you want to know whether something is at redshift of 6 or redshift of 4, you can't have 100% error. So going from 10% to 100% is fairly significant. Back before the redesign efforts, I would have a slide in talks I would give about how we're weak lensing limited. We can't hope, or we can hope, but at present we can't get any lower than a certain level. Something like 3% fractional error at a redshift of 1 or 5 or something. I don't remember the exact numbers, but the punchline being, there's a natural bound that has nothing to do with the statistical uncertainty from the gravitational wave measurement. You'd really like to push down to that bound. Ideally, you don't want your cosmology measurement to be limited by the gravitational wave measurement. And there are lots of proposals to improve the weak lensing bounds by shear deflection, all sorts of elaborate ways of mapping out the matter in between and trying to subtract away that effect. But assuming that things are still the way they are now, when ELISA flies, it would be lovely to have that be the limiting factor. I emphasize very, so as I mentioned, people, myself and the group at Goddard are working on this. I believe Neil and Emanuele also looking at combining all of the physical effects we just listed. So far, I only have extremely preliminary results for example cases. I haven't parallelized and got everything running where I can do one big coherent run with all of physics. But for specific cases, it seems that combining a precessing in-spiral with the higher harmonics, adding that to the Fisher for an aligned spin merger with higher harmonics doesn't have an enormous effect, doesn't improve things by an order of magnitude. Now, that could change once I more rigorously do these things, but so far it's not looking promising. Also, another thing you could imagine is that if you have an electromagnetic counterpart, well, you can't assume the cosmology, well, you can, but you'd ideally not assume cosmology and convert the redshift to a luminosity distance and try to back things out that way. But you can say, okay, the electromagnetic signal is giving me a very exact angular location. So I know that, so that will kill any degeneracy between that angular location and the luminosity distance, something like this. That doesn't seem to help enough either. Remember, we're talking an order of magnitude effect. So bottom line, this is really the last slide, and I'll put up the conclusions. So classic ELISA was really a near optimal design. It's hard to compete with that. It was so good, in fact, that prior to the redesign studies, there was a lot of physics that was known, but that just hadn't been included yet in the parameter estimation. It's not an easy task. It's kind of tedious in a lot of ways, so that's part of the reason why. However, with the 4-link design, it seems that we really need to include all the physics we know to tamp down these errors as far as possible. So the margin that we had from having such a good instrument needs to be made up for somehow, or we want to make up for it somehow, and the obvious place is the physics. We have some time, so maybe we can develop some more physics. It's not going to fly tomorrow. It's going to be a little while. So maybe we add more physics and we get even further improvement. And of course, 6 links would be lovely. So if that's ever a possibility in the future, due to some fortuitous change of budgets and realliances, then great. So in conclusion, we can still do extremely high precision measurement, really of any parameter depending on which population, which configuration, et cetera, you pick. If you pick the best histograms in particular from all of these studies, the best case scenario is incredibly precise measurements in every parameter. Now you can imagine less precision in things like luminosity distance, so that's where the concern lies. So previously we had adequate precision in every parameter without having to worry too much about what physics was included, but now we really need to include all of them, all of the physics we know. The results that the task force has come up with, these are just some rough, very rough numbers to keep in mind. So individual masses, are measured fractionally to 0.1 to 1% accuracy, distance to 10 to 100%. Individual sky angles, and this can be pushed down a little bit further actually. For some cases, we're still getting around a degree. And then spin magnitudes extremely well. Are these good enough? So again, in the discussion session, it would be nice to talk about what is really needed